Hi there, my name is Macklin Leah Bialy, and I'm going to take you through machine learning in Python. So we are going to look at the introduction, the different types of machine learning, the machine learning pipeline, the algorithms, the support vector machine, the principal component analysis, and also at the end, we shall look at the problem we can solve using all this knowledge. So talking about machine learning, this is a field of study that gives a computer the ability to learn without being explicitly programmed. In this case, we can give an example whereby you give a particular task to a computer program and it performs this task repeatedly. So the more it performs this task, the more experience it gets. And the more experience it gets, there will be an improvement in its performance. So why was machine learning introduced? Initially, we had traditional programming whereby the users or the programmers struggled with writing rules for given programs. For example, if you're having a small program like for a traffic light system, we shall use if-else statements. So for example, you can say if the button is red, then stop, else button green, then go. But if we are having a very complex program or complex problem, then traditional programming will not work out. So therefore, we shall have to use the machine learning method. So we have different types of machine learning. For example, supervised learning, which requires a human-labeled data set. And in this case, you get the data set you're having, you put it into the machine learning algorithm so that this algorithm can be able to make predictions. So some of the machine learning problems, you have regression, which predicts continuous numerical values, for example, the price of the house. Then classification, it also learns to assign data to predefined categories or labels. For example, an email can be spam or not spam. Then we have another type of supervised learning, another type of machine learning called unsupervised machine learning. So this enables a machine learning algorithm to learn without labeled data set. So we shall have features in the unlabeled data set representing information, and the model will study these features so that it can be able to gain patterns. And from those patterns, it will be able to make informed predictions or informed decisions automatically. So in this case, we shall bring in the clustering term. For clustering, this one involves grouping models together, or you're grouping, the model groups features together according to the exhibition in the same characteristics or patterns. So we also have anomaly detection, whereby the model detects an unusual occurrence. For example, in finance, if we are to detect fraud, a given credit card may be being used to withdraw a particular amount of money in a given range. But there comes a point of time whereby this credit card is being used to withdraw a very huge amount of money. So in this case, that will be an anomaly for such an algorithm. Then the machine learning pipeline, the first step is data collection, or you're going to get your data. Then after you perform the exploratory data analysis, that's the EDA, this should be quick, efficient, and decisive. So in this case, it will involve plotting, whereby you plot the numerical distributions with the histograms, and also you plot the categorical distributions such as the bar charts. Then the third step will be preparing data for machine learning algorithm. And as we are preparing the data, we can use feature scaling, and this can be done in two ways. That is data normalization, whereby you're going to fix the data values in a given range, or it can be data standardization, whereby you're going to transform your data to have zero mean. But why do we scale? We scale because machine learning model only sees numbers, and we only scale when using machine learning algorithms that calculate distance of the data. Also, when we're using the neural networks and maybe principal component analysis. So we have different types of scaling. We have the min-max scaler and the standard scaler. So another way we can do the data preparation is through data cleaning. So here you're going to clean your data in case you're having maybe noise in your data. For example, the car health monitoring system problem we are going to be having at the end of this, we shall have to collect our data. We shall collect the different sounds from cars in different conditions, and from that we shall have maybe, let me say, the frequencies from these sounds, we shall have the amplitudes from these sounds. So from that data collected, we shall have to denoise our data, and that is what we call data cleaning. So we also have feature engineering, whereby we shall study the features. We shall combine, remove, or even add other features. So the fourth step in the machine learning pipeline is selecting a model and training it. First of all, every model has to have three things: the prediction model, which takes in input features and predicts the output; the cost function, whose result is the difference between the actual value and the predicted value; then the optimizer, which adjusts the weight to get a better cost so as to make the improved decisions. So gradient descent is an optimization function you can use in this case. We are having a linear regression model, which is a representation of some phenomenon. So types of the stats model, we have the deterministic models. These ones work with ordinary fixed values, therefore there is no randomness. Then the probabilistic models, this one works with randomness, and under this we have the regression, correlation, and other models. So we talk of logistic regression. This one is used for classification problems. That is, of course, when we are having categorical data. So another step in the pipeline, we have fine-tuning the model, then you present the solution and you launch, monitor, and maintain your system. So under machine learning algorithms, we also have supervised learning algorithms, the ones which require labeled data. For example, the k-nearest neighbors, the decision trees, and ensemble learning. Then under unsupervised, we are having these are the algorithms that work with the unlabeled data. For example, clustering. So talking about the k-nearest neighbors, we shall have the parametric models, which tell the model exactly how you'll fit to the data. And then the non-parametric, these ones will tell you what regression should look like. So these are the different steps for the KNN. And talking of Euclidean distance, it is used if dimensions are measuring similar properties, yet for Manhattan distance is used when measuring dissimilar properties. So talking of decision trees, it involves output prediction by recursively splitting data based on feature conditions in a tree-like structure. So we have the decision iterative dichotomizer. This one dichotomizes or divides the given feature we'll be having. So you'll find the best feature. Best feature will mean that you're getting that feature which has the most important values or the most important target. Then after that, you'll find the best split for the best feature. Then you partition classes based on steps 1 and 2. So comparison with the sklearn decision tree, sklearn can't handle categorical data, which yet the ID3 can do that. So that is where the trade-off comes in. So the Gini and entropy, these are impurities. Gini index has values between 0 and 0.5, while entropy has an interval 0 and 1. So since we are talking of decision trees, we shall also talk about pruning. Pruning comes in a way as to avoid overfitting, and it can be done through pre-pruning, whereby you're going to prune or you're going to remove the extra branches or nodes from a given tree before it grows fully, or you can do it through post-pruning. And in this case, you're going to allow the tree or you're going to allow the branches to grow fully, then you come back to remove the unwanted or the unnecessary branches or nodes. So for pros of decision trees, it is easier to interpret and visualize and can easily capture nonlinear patterns. Then for the cons, it is sensitive to noisy data. Small variance in data can result in different decision tree. So talking of ensemble learning, it involves combining many weak models to form one superior model. And the limitation here is that there is an assumption that all predictions are completely independent, which is not realistic at all. So the solution we have here will be bagging and boosting, whereby in bagging, that is, you're having the parallel training of different models using the overlapping and training sets. Then for the boosting, it is the sequential training by iteratively reweighing training sets examples such that each model focuses on a different subset of examples. Talking of bootstrap aggregation, what is it good for? It is good for reducing the variance of the models, thus reducing overfitting, and outliers are likely omitted in some of the training bootstrap samples. So these are the bagging steps. Then talking of the out-of-bag error, it is an internal validation method used to estimate the test error without a separate validation set. And because of this fact, there will be no need to use cross-validation to get an unbiased error estimation, since in bagging the error estimation takes place internally. So the random forest, here you'll be having your full data set, and from this data set you'll get random samples from it. That's why we call it a slightly modified bagging algorithm. After getting those samples, the model will work with these different samples. Then from the predictions from these different models will be gotten, and we shall get the average of the three. Then we take that as the result. So the pros of random forest: first of all, robust to outliers, works well with nonlinear data, runs efficiently on a large data set, low risk of overfitting. Then the cons: we have biased while dealing with categorical variables, slow training, not suitable for nonlinear methods, and others. So for the application you have of random forests, we have cargo computations and text mining, then others. So in boosting, we have the adapt boost, call it the adaptive boost. Here you're combining multiple weak classifiers to build one strong classifier, with each one progressively learning from the others wrongly classified objects. So here you're having your different models, but for the different model, in case you're going to work on a new on a new model, you give it only the mistakes or the wrong things the previous model has done, so that this new model can perfect the mistakes. Can correct the mistakes done by the previous model. So bugging versus boosting. Bugging is easy to parallelize, and hence training is faster, while boosting is more efficient for fixed number of interactions. So clustering, we talked of this as grouping, finding similarity groups in data. We have two different types: partitioning clustering, whereby the k-means clustering falls, and for the k is specified by the user. For example, we can say maybe you're going to have three means clustering. It means that if you're having your given data set, you're going to divide that data set into three partitions or three groups. Then the other example is hierarchical clustering, whereby you're going to produce a nested sequence of clusters, a tree, also called dendrogram. So we are having these types: agglomerative clustering and divisive clustering. So we have the support vector machine. What makes the best hyperplane? You can call a hyperplane a best fit or a line of best fit. So what makes it a best one? So first of all is correct classification. If you're having a group of oranges and a group of mangoes, and we want to divide these two correctly, like we want to have a line of best fit between them, then we have to first correctly classify them. You have to correctly categorize and group them. So we also have maximization of boundaries, whereby this line of best fit we are going to use, it shouldn't be so near to the group of mangoes, and it shouldn't be so near to the group of oranges, but it has to be in the middle of them. So we also have outliers, whereby in case you're having the orange, one orange in a group of mangoes, you may decide to either consider that or not consider that. And that's where hard and soft margins come from. Hard margin requires perfect separation. So hard margin is so strict in that in case we are having any given outliers, you have to consider the outlier and work it to the best. Then soft margins, it is not that strict, and therefore it generalizes better. So we have the C parameters, which control overfitting. Gamma parameter controls distance of influence of a single training point. So we have the SVM kernel. These are the types of it. Then principal component analysis. This one is used to reduce the number of features in a dataset. For example, the car health monitoring problem we are having in this case, whereby if we have collected the data with the frequency, the amplitude, and the different types of values for the different features of the cars, then we can decide that in case a feature is having almost many similar values for each case, then we shall have to go away with that feature, and therefore we shall have reduced the number of features in our data set. So the drawbacks: it assumes that variables are linearly correlated, which may not be true for all cases. Then it performs lossy compression. Scaling of variables can yield different results. Then the main applications of PCA: we have image compression, pre-processing step for classification, facial recognition, and data visualization. So this is the problem we are working with, whereby if we are having a car, we are having different cars in different conditions, then we shall have to collect data from them. We shall collect data from maybe a car having a problem when it's about to run out of fuel. When we shall also have to collect data from, collect sound from the car which maybe is having a faulty engine, a car from which has all these problems you're going to work on. So after that data collection, then we shall have data preparation, whereby we shall denoise our data. That's cleaning the data. Then we can still use the PCA, the principal component analysis to reduce the different features in case for a given feature it has almost similar values for each row. Then we shall train our models. We may use decision trees or even ensemble learning. Evaluation, whereby we shall check the accuracy and recall. Then for prediction, we shall have our models to fully predict the NUCA sounds automatically. And as long as they can predict the sounds automatically and very well, then they can give us alerts in case of any condition so that we can be able to go away with it before the problem arises. Thank you for listening.